Hello everyone, how are we doing today? I forgot to fix that. Alright, so how's it going? Seems alright. Before we get into other material, I wanted to see if there were any questions that you all had about stuff that was on the take-home exam. Yes. So for finding the fundamental subspaces, there are multiple techniques that you can use. Um, as long as you pick a valid one, I'm not going to be picky about what it is you do. So when we covered this in class, I mentioned that there were a couple of different techniques for how to set things up. The the way to you can at the same time find the bases for the column space and the row space, or the column space of A transpose, is the way that it's written, by placing the matrix in reduced row echelon form. So, or at least in row echelon form, but I think reduced row echelon form is a better way to go. You what you do is, if you identify the pivot columns, then you take the pivot columns from the original matrix as the basis for the column space, and then the rows that you are left with in reduced row echelon form are the basis for the row space. So you get those two things kind of immediately, and then you find the null space, of course, by finding a basis for the solution to the homogeneous equation. Does that answer your question? I mean, it changes which one's the row space and the column space, but yes, as long as you keep it organized, then if you want to solve the problem for the transpose instead of solving the problem for the original matrix, that's fine. But if you place either A or A transpose into reduced row echelon form, you can, by looking at reduced row echelon form, write down the answer to both the questions: what's the basis for the row space and what's the basis for the column space. Both pieces of information are immediately available if the matrix is in reduced row echelon form. One by identifying the pivot columns, the other one by just taking the rows that you have from reduced row echelon form. Is that good? Okay. Is there another question? Yeah. Okay. Sure that we're looking at what's going on with. Okay. For number 4, I ask you to talk about some subspaces. I give you a basis for a subspace S, and then I ask you some questions about its orthogonal complement. The orthogonal complement should be composed of vectors that are orthogonal to the original body, and what I want you to do is to describe to me what those subspaces look like. Okay, what's their relationship? What shape do they have? Since we're starting off with R4 as the ambient vector space, okay, each of those subspaces should be some subset of R4. So tell me what they look like and what the relationship is between those subspaces. You can't really draw a picture because it's a four-dimensional ambient space, but you should be able to describe in words what's going on with the pieces. For part C on that problem, what you need to do is find the matrix whose column space is S complement. That's the answer. Okay, and there's a way that you can. It's shouldn't be that hard if you think about what's going on, but you can puzzle out how to construct a matrix P that gives you that column space. Okay, now obviously you want the matrix to map vectors in four-dimensional space to four-dimensional space. So the matrix is going to need to be a 4x4 probably. Okay, so you need to create the correct 4x4 matrix that has the same column space as whose column space is equal to S complement. So find a basis for S complement, and then using that basis, you should be able to construct the appropriate 4x4 matrix. All right. Other questions? All right. So, over the weekend, I posted materials, making sure I was caught up on the Chapter 5 notes and everything. And then I also posted this so that everyone could have an idea of kind of what a rough outline of topics were for stuff that would show up on the exam. So we have this material here to take a look at. This is going to be what I'm working off today, talking about what's going on. I sent out an announcement about this in Blackboard, so there shouldn't be any surprises on here. And the way that the test is going to be formatted is very similar to what we had for exam 1. There's going to be a couple pages worth of questions having to do with either true or false or mark all that apply kind of things based on those topic subcategories. So we'll have, there'll be questions about vector spaces. There might be questions about vectors that form a basis. There might be questions about orthogonality. Okay, and for those, I'll give you some condition, and then it'll be your responsibility to mark all the things that are also true as a consequence of the property or the situation that I described. Okay. And then for the other part of the theory questions, we'll talk about true false. Those require, of course, identifying if something is true or false, and then also giving either appropriately a justification why something's true or false, or if it's false, you can also provide a counter example. Just cough up a situation where the idea in question fails to be true. Okay. So there's 2 pages of that material. For the short answer stuff, there's 2 pages of this. I call them short answer because they're short computations. All right. There will be multiple questions asked on a page as opposed to one long computation to do, like you would see if I ask you to solve a system or to set up some kind of problem or something like that. Okay. For these, it's going to be more about whether you know what I'm asking you is about than it is doing a long form computation. So there might be questions here that concern identifying whether or not something is a subspace. Okay. There may be questions here that concern inner products and computations involving inner products. Obviously, the idea of orthogonality is very important when we're talking about inner products as well. That's a big theme for the exam overall. There's also the concept of dimension, maybe something that comes up. And then I mentioned orthogonality and bases, and orthonormal bases could also be relevant. The last couple of pages will be longer form computations, where I ask you to go through and do more stuff. Okay. For the longer form computational questions, inner products are a theme throughout the exam here. So if I haven't asked you enough questions about inner products by this point, then there will be more questions about inner products here. Other stuff that can come up for these types of questions are going to be things related to solving the least squares problem. Okay, that's our probably most important application as far as solving a practical problem would be to find the least squares solution. That gives us answers to overdetermined systems, which when we're working in the real world are the kinds of systems that we tend to get. All right. You take many, many, many data points, and then what you try to do is come up with a model that represents that data set. And the way that you do that is by using linear algebra and solving a least squares problem in a lot of cases. All right. I know you've all seen dozens of different examples over your lifetime of people solving line of best fit problems. All right. That's just the simplest case of solving a least squares problem. All right. There are many other types of linear algebra problems that are similar. Okay. On the take-home exam, there are problems where I ask you to take a look at Gram-Schmidt orthogonalization and the QR factorization, as well as looking at transition matrices. Okay. Those are also important ideas. If on the in-person exam I ask you to solve a least squares problem, I do not care what method you use to do it. We have discussed that both QR and forming the normal equations are ways to solve the least squares problem. So if I just say solve the least squares problem, you can do whichever one you choose. All right. I will let you know that for the sake of time, I'm probably not going to ask you to do a Gram-Schmidt orthogonalization on the test, just because that takes so much of the time budget for the exam, and those computations are kind of tedious. They're never clean. So if you want to solve the least squares problem that way, you can. All right, but I'm probably not going to require it because we've already got that question on the take-home test. All right. Now that isn't to say that there won't be a least squares problem, but it's solve it how you choose. All right. Make sense? Okay. So what I want to talk about to start off with are some of the true-false questions. The true-false questions for the exam are being pulled from the true-false questions in the chapter reviews. All right. We're going to talk about some of these, not all of them. And then after we talk a little bit about the true-false stuff, then we'll look at the more computational type things. Okay. Okay. So true or false? The standard operations in Rn are vector addition and scalar multiplication. True or false? I've got a couple people who believe that it's true. What do the rest of us think? This seems like it's obviously true. Okay. All right. I've noticed this, that when we write down things that are this seemingly fine, everyone has been trained to be really skeptical and assume it's somehow a trick question. Anywho, this is true. All right. The standard operations of vector addition and scalar multiplication are the standard operations in any vector space. Okay. And the whole point is when we have a vector space, we need to have an operation that is the operation of vector addition and an operation that is the operation of scalar multiplication in order to define how a vector space works, right? Our closure properties have to do with vector addition and scalar multiplication, and our 8 axioms of a vector space each have 4 that are devoted to each of those operations, right? For addition, we need addition to be associative and commutative. We need an additive identity to be in the vector space, and we need all the additive inverses to be in the vector space, right? Those are the 4 axioms for the vector addition side. And for the scalar multiplication side, we need scalar multiplication to distribute over scalar addition and vector addition, and I have to remember. We need the multiplicative identity for scalar multiplication, and we also need that 0 times a vector is 0. I think that's the 4. Some of them you can back around and do different ways, like one implies other or whatever, but I believe that's the list. I think you need the multiplicative identity, the multiplicative annihilator, or the 0 multiply by 0, and then I should look this up. And then scalar addition and vector addition. Save this page. Nope, I was wrong. Sorry. The two, you need the two distributive properties, and you also need the associative property of scalar multiplication. And 1 times a vector is the vector. So you need the scalar multiplicative identity, but you don't need, you don't take as an axiom that 0 is an annihilator. that was where I was wrong. Anyway, sorry. So the one, that's the, we need associativity for scalar multiplication, was the one that I forgot when I was listing them out loud. Okay. All right. True or false? The set W equals vectors composed of 0, x squared, and x cubed for some scalar x is a subspace of R3. How is it that I verify whether or not something is a subspace? Sorry, what? We need to check the closure properties for these vectors. So we're looking at vector addition and scalar multiplication, and you say the closure properties, but what specifically do I need to make sure that this is closed under or closed within? The operations, vector addition, and scalar multiplication, that's correct. But when I'm checking for closure, what do I want vector addition and scalar multiplication to give me? If I add together two vectors in W, what must I get? Pardon? I can't hear you, I'm sorry. Not a vector in R3, a vector in W. It's closure within the subspace. Okay? I think you knew that. I just want to make sure that we said it. All right, anyway, so we have to make sure that if I take a vector and multiply it by a scalar, or take a vector and add them together, that I end up with something in the subspace. So multiply by some scalar, alpha, I guess. Is this in the subspace? What does our subspace say has to be true? The number in the second entry has to be some number squared, and the entry in the third space has to be that number cubed. Is this true? It's not, right? Because I would end up with the square root of alpha cubed. So the relationship between these entries is not the relationship that's specified by my vector space, or my subspace, pardon me. Okay? So it's a little hard to see if we did scalar multiplication. Shows that we're not closed, all right? It's obvious if we do vector addition. Is that sum in W? No way, right? Okay. This gets us into the territory where we'll start asking questions about Fermat's last theorem, right? The second entry is the Pythagorean theorem. Maybe that's okay. The third entry, absolutely not, because we don't have a cubed plus b cubed equals c cubed, right? That's not something that works that way. Okay, so that one's false. All right. The bigger lesson here, of course, is that whenever we're identifying subspaces, check the closure properties. If something's a subspace, then it'll obey the vector addition and scalar multiplication closure properties. Now, it isn't a guaranteed check that this will always tell you if something is a subspace or not, but the easiest way to reject a potential subspace is if it doesn't contain the zero vector. Okay? If I ask you if something's a subspace and it doesn't contain 0, then it can't be a subspace. All right? But that only tells you when something's not a subspace, whether or not it is. All right? There are plenty of things that have 0 in them that are not subspaces, like this one. The 0 vector is part of this, but it fails the closure properties anyway. All right. Is it true or false that the additive identity of a vector space is not unique? Agree that it's false? Okay. How do we prove that it's true? Sorry, pardon me. How do we prove that the additive identity is unique? Pardon? All right. That is the standard way that we prove something is unique. Suppose there are two. So we're going to suppose that U and V are additive identities. Okay? If they are additive identities, then I can add on either side, and I have to get the original vector back, right? That's the proof. Okay, now this is um, one of my math professors referred to this kind of thing as a swindle. All right, it's one of the so-called standard swindles that you learn when you do proofwriting. In some classes, all you would need to write is actually that little equation there, and you'd be given full credit for the proof. Because if you know that, then, or at least this much, okay, telling people what U and V are. All right. The reason that this works is because A is allowed to be any vector, right? Okay. So for the first part, I'm using this equation here. U is A. Sorry, I'm using this equation here. U is A, and then I add V to it, but V is the additive identity, so U plus V is equal to U, right? And then on the other side, I use this, except in this side, A is V. I have used the property that both U and V are the additive identity, and in doing so, demonstrated that they have to be the same. Okay? Anytime you're talking about some kind of identity or identity element, this is how you show that they're unique. If you were trying to show that you have a multiplicative identity and the multiplicative identity is unique, that's the proof. Okay? It's one of those things that's so simple it can be difficult to see what to do, right? Also, in general, if I want to show that something's unique, I assume there are two and prove they're the same. That's the other part of this. Yes. All right. I'm allowed to write this, right? I'm allowed to pick any vector I want to represent A. A is just a generic vector in the vector space. Okay. The vector I pick is U because I want to say something about it, right? So U is equal to U plus V because V is an additive identity, right? That's how I get this part. Then U plus any vector is equal to that other vector because U is an additive identity, right? So U plus V has to be V. But I have U all the way on the left and V all the way on the right, so U has to be V. So in this central line here, this is the swindle that I was referring to. I'm using the property of U being an identity on the left and V being identity on the right to show that U has to be V. Okie dokie. Those were chapter 4, true false questions. We're going to do a couple from chapter 5. All right. One thing that I want to mention, just so it's been said, so people don't freak out about this, your book spends a lot of time in section, I think 5.6 in particular, talking about cross products. Okay, we haven't spent any lecture time on cross products. There are several true-false questions about cross products. All right, I'm not going to ask you about those because we haven't spent time talking about cross products. All right, so the true-false questions, don't worry about the stuff about cross products. You've taken physics, everybody in here, I'm pretty sure. All right, the calculus-based physics. I know that you covered some material about cross products probably at the beginning of, if not at the beginning of Calc 2, you'll definitely talk about cross products in Calculus 3. All right, you will get as much exposure as you need to that idea. I'm not worried about it right now. We're much more concerned about inner products because inner products are more deeply tied into the applications and stuff that are relevant to us in this course. All right, all that out of the way. All right, so true or false? The least squares approximation of a function f is the function g in a subspace W closest to f in terms of the inner product between f and g. So we have to ask ourselves a question about what's going on with inner products. Okay, geometrically, what does an inner product do? What is its purpose? Vectors have magnitude and direction. Okay. All right. We very recently talked about Gram-Schmidt orthogonalization, right? As part of the Gram-Schmidt orthogonalization process, we compute a lot of inner products, right? Now, what are we doing when we compute the inner products for the Gram-Schmidt process? Because Gram-Schmidt is something that we can use to solve the least squares problem, right? If I do Gram-Schmidt and I get a QR factorization, I can solve the system from the QR factorization, and that gives me a least squares problem. Yeah? Okay. So when I'm doing QR and I'm computing those inner products, what do those inner products represent? There's an important word that starts with a P. They are projections. Okay? An inner product is a projection. All right? What it is if I take the inner product of f and g, it gives me the projection of the vector f onto the vector g. All right? It gives me the overlap of those things. It tells me how much of one is in the direction of the other. Right? Okay? Now, we can use inner products to define a notion of angles, right? And if these vectors are orthogonal to one another, that is, the angle between them is pi over 2, then there is no element of f in the direction of g, so the projection's 0, right? If they're the same vector, then the projection is entirely in the direction of the other function, right? And I get the square of the length, right? Because the inner product of f with itself is the square of the length of that vector. All right? So, when you think about an inner product being computed, you should always think about it as some sort of projection. All right? That's its geometric purpose. All right? So, returning to this question here, if I have some function g that lives in the subspace W, that's the least squares approximation, is that the vector that is the closest to f in terms of the inner product? By definition, yes. Okay? G is the projection of f onto each of the basis vectors of W. Okay? So W is the span of some set of basis vectors. Okay? And G is given as the sum of f projected onto each of these. Okay? This is how we define the solution to the least squares problem. All right? So if I have some kind of projection matrix or some system defined, the solution to the least squares problem is the vector in the column space of the linear transformation that's the closest to the right-hand side. Okay, F here would be the analog to the right-hand side. Make sense? Okay. All right. So, um, overview of some true-false questions. All right, to get us kind of in the headset or the mindset of what do we need to be thinking about to solve these kinds of things. A couple of them I chose will be the ones that you see on the test. Other ones actually cover different ideas that show up elsewise on the test. All right, review the true-false questions to make sure that you're familiar with the ideas. But I've told you that the true-false ones aren't going to be, or the cross-product questions are not going to be asked about. Don't worry about the cross-product ones. There's 10 to 15 other ones. Look at those. Or 10 to 15 total, pardon me. All right. Questions? Yeah, sorry. I'm probably not going to be. I'm not going to be framing questions that way. All right. Um, so I don't. I didn't. I didn't type any union or intersection symbols on the exam. Yeah, 5. That 5 is how many fit with the font size that I chose for the test. Okay. 25 minutes left. Okay. So let's talk a little bit about inner products. All right. So let U1 and U2 be an orthonormal basis for R2. Okay. And I want to define a pair of vectors, x and y, like so. So x is equal to 3u1 minus 2u2, and y is equal to 4u1 plus 2u2. Okay. And I would like to determine the inner product between these two vectors. How do I do that? I'll just write it out, right? So if we want to work this out, all right, the main idea is we have multiple properties for matrices, or sorry, multiple properties for inner products. One of the properties for inner products is that the inner product is multilinear, right? So what we can do is we can start breaking this up into its pieces because it has to obey the properties of multilinearity. So for instance, this has to equal this. Okay, sorry, ran out of room there, but same thing on both the second parts. We apply multilinearity again. We get this, right? Okay. Now, just as an aside, the multilinearity property also says that this has to be true, right? And this. So that allows me to take 3 times 4 plus 3 times 2 minus 2 times 4. And we get to this, right? So what's the answer? U1 and U2 are orthogonal to one another. Right? Okay. Now, we have saved ourselves a whole lot of work if we had just done that. Okay? Now, the only reason why that's true is because we have an orthonormal basis. All right? Otherwise, it would be necessary to perform this full calculation. This is one of the great values of having an orthonormal basis in our inner product space. Okay? Inner products are what is known, or what have the property of being coordinate free. All right? The value of an inner product in an inner product space between two vectors is always the same. Okay? It does not matter the coordinate system with which I have represented x and y in this case. The inner product of x and y is always going to be the same number. All right? If I have an orthonormal basis, that number is easy to compute because I have an orthonormal basis for Rn and I just do the dot product. Okay? If I don't have an orthonormal basis, then it's necessary for me to deal with this, right? And if the inner product of U2 and U1 is nasty, then I have to figure out what that number is. I have to determine the projection of those vectors, right? Get that value and go from there. Okay? Vectors are the quantities that depend upon the choice of coordinate system, the choice of basis. All right? They have expressions that are tied to a specific selection of coordinates. The underlying quantity being represented by that vector is always the same. Its magnitude and its direction, right? Those are the things that we know define what a vector is. But magnitude and direction are both measured by the inner product. Angles between vectors we get because we have an inner product. The length of a vector is expressed by using the inner product. All right? So it is the thing that has sort of the fundamental identity-giving properties, not the coordinate system. We're used to thinking about the coordinate system and the coordinates of a vector as the thing that we use to name a vector. That's actually backwards. Okay? The coordinate system comes second and can be changed. All right? There are infinitely many valid selections of a coordinate system. All right? They all represent the same information, but they give everything different names every time we change it. All right? There is one choice for an inner product in an inner product space, and once we choose that inner product, all of those values are fixed for particular objects. The inner product between two vectors is always going to be the same number if those vectors don't change, even if I change the coordinate system. The underlying vectors have the same relationship through the inner product. Okay? And as we just saw in this example, inner products are very easy to compute for orthonormal bases, which is why we always, whenever possible, work with an orthonormal basis. And sometimes jump through a lot of extra hoops in order to force our bases to be orthonormal so that we have the most convenient version of arithmetic to work with in our environment. All right. Questions about this? Seems all right. Okay. Okay. One of the questions that shows up on the take-home test has to do with transition matrices. Okay. Want to make sure that I clarify what's going on with this here. So let's choose some basis t here. It's a basis for R3. Okay. It's not orthonormal, but that's okay. All right. Now I know I just spent a bunch of time extolling the virtues of an orthonormal basis, but we don't always necessarily have one of those. Okay. Here's just a regular old basis. But what we want to make sure that we understand is how to interpret a basis in terms of transition matrices. So I, of course, can write down a matrix T. That is a transition matrix associated with this basis. All right. But the association works in a sense that is perhaps counterintuitive for us. Okay. This is the transition matrix from t coordinates to standard coordinates. Now, you would maybe think that it should be the transition matrix from standard coordinates to t coordinates, but that's not how it works. Okay. The idea here is easier to understand if we return to the notion of thinking about matrix multiplication as a linear combination. Okay? So if I write down this multiplication here, I have our matrix T times a vector T1, T2, T3, and that's going to be equal to, on the right-hand side, x1, x2, x3. All right? This is in T coordinates, and this is in standard coordinates. All right? The way that we should think about this multiplication here is I am taking a linear combination of the columns of this matrix. Okay? When I take this linear combination, what I'm doing is I am performing a matrix multiplication, and the value that I get on the right-hand side are my coordinates in the standard basis. So the x1, x2, x3 standard basis. The T1, T2, T3 are the coordinates in the T basis for this vector. All right. And this fundamentally is how we should be thinking about what coordinates are and how they work. Coordinates for a vector are a linear combination. The coordinates that I have for a vector are the coefficients for the linear combination of the basis vectors. That's what they are defined to be. They are the numbers that I multiply the basis vectors by in order to represent my vector. Okay? So earlier I was talking about how the representation of a vector is tied to the choice of basis. Right? This is what I mean. Okay? The thing that makes a vector is its magnitude and its direction. Okay? We represent vectors with respect to coordinate systems because that's the most convenient way to do it. Right? But that representation is tied to the choice of coordinate system. And the choice of coordinate system can change. All right? The choice of an inner product never changes once we make it. Okay, it's fixed. So when we set up these computations, this is the way to intuitively understand why it seems like I'm going backwards. I multiply by a matrix T whose columns are the basis vectors for the T basis. And what that does is it takes me from the T basis to the standard basis. Okay? Now, if I want to go the other direction, that is from the standard basis to the T basis, what do? We multiply by the inverse. Right? Now, some jerk asked you on your take-home exam to, instead of going from the standard basis to a different basis, or from a different basis to the standard basis, go from a non-standard basis to a different non-standard basis. Okay? So how do we do that? Okay, so that's a computational method that will produce the transition matrix between the two non-standard bases. Okay. The procedure, the idea that we're following is going from non-standard coordinates to the standard basis. And then what you want to do is go from the standard basis to some other coordinate system. All right? This multiplication is applying the matrix T to go this way. All right? What if I have some other basis named S, what must be happening here? If I wanted to go from standard coordinates to T coordinates, what would I do? Okay, start with the first question. What did I do to go from T coordinates to standard coordinates? I multiplied by T. Okay? If I instead want to go from standard coordinates to T coordinates, what should I do? Multiply by T inverse. Okay. So if I have some other basis, S, and I want to go from standard coordinates to S coordinates, what should I do? I multiply by S inverse. So if I want to go from T coordinates to S coordinates, I should go from T to standard and from standard to S, which I do by TS inverse, right? Now I write that as S inverse T, but I multiply by T on the left, and then I multiply by S inverse on the left, right? Okay, because matrix multiplication proceeds this way, to the left. So the rightmost matrix multiplication happens first, right? But you have to get the order right, otherwise it won't do what it's supposed to do. Now, there was someone who described a procedure in the textbook that they found probably while thinking about this problem. Okay, using the letters that I've been writing here so far. One of the things that you can do is you can make this augmented matrix, right? All right. And the idea would be that you would have the transition matrix you want after performing the necessary row operations to turn the left part of this augmented system into the identity. All right. The reason that works is because the thing over here ends up having to be S inverse T. Because in order to get the thing on the left of the augmented matrix to be the identity, is you have to apply the sequence of row operations necessary to construct S inverse, right? So the matrix on the right, T, ends up being multiplied by all of the things whose product is S inverse. That's why this method works. Okay, you are constructing S inverse through elementary row operations, which is a thing that we know from all the way back in our first test is true, that invertible matrices are equivalent to a product of elementary row operations. That's the whole idea of row equivalency, right? All right. So how are we feeling? Seems good? Okay. All right. So we'll come back next time. We'll have our exam for the take-home, or sorry, the take-home part's due this evening, and then the in-person part we'll do on Thursday for you all. Think I'm excited to see how everyone does. I was very, very pleasantly surprised by how everyone did on exam 1, so I expect everybody to do just fine on this one too. All right. But if you have any questions, of course, email me. I'll do my best to make sure that I answer those as promptly as I can, and then I will see you all next time.